Sorry, I'm late getting started by a minute. We're writing this big proposal to take over the world with CS10, and today's the deadline. And the institution we're collaborating with on the East Coast had until 2 o'clock our time to submit, and as of 12 minutes of, they hadn't done it yet, so things are a little rushed. Okay. So last time, oops. Oh, wait. I'm in the wrong place. Oh well. So we left off last time with this kind of miraculous result. Yeah. Oh, you don't see anything. Huh. Oops. No, that's not what I want. That's what I want. There we go. Thank you. So this very miraculous result right here, in which there are exactly 6 different ways to append 2 lists to get the result A, B, C, D, E, and the query system found all of them, working with what's essentially just a rephrasing of the scheme append procedure. But the scheme append procedure only runs forward. You say 2 little lists, and it gives you a big list. And somehow by couching it in logic programming terms, we get a relation that can figure out the constraints forward and backward to give you what you want. Now, it can't do something that can't be done. So if I gave it 3 variables, so append question mark x question mark y question mark z, it's going to run forever, giving me sort of gibberish results. So there has to be enough information in your query that it really does constrain the problem. Also, I should warn you that not everything works backwards. So one example that you're going to see in the homework or in the lab is if you try to write a reverse set of rules, a reverse relation in the obvious way, reverse this list, that list is true if one is the same as the other, only with the elements in the reverse order. You're almost certainly going to end up on your first try with something that works in one direction but doesn't work in the other direction. And I think the extra for experts this week is to try to come up with a version of reverse that really does the job bidirectionally. So what that means is that this abstraction, as we're presenting it here, is not perfect. So in order to make sure your program works, you have to think a little bit about how does the query system actually do the job that it's doing. I should say that this is a little toy query system that Abelson and Sussman wrote just for the purposes of this class. If you look at a real logic programming language, they've made great strides in being able to solve some of these problems, but I think it's still not perfect. Sometimes you have to help it out a little bit by saying, okay, don't go down here. If you do, you'll get in an infinite loop. So we want to see how the query system works. That's our job today. And I guess there's 2 pieces to that. And let me start with the piece that is sort of big in scope, which is sort of stepping back and looking at the big picture, which is right here. So here's schemes evaluator. It takes two arguments, an expression and an environment. I've drawn the environment off to the side because if you think about what it is you really want from Scheme, you give it an expression and it gives you a value. And the fact that there's an environment involved is just sort of a detail. So this is sort of the main pipe through here. So I want you to compare this, which is Scheme, with how the query system works. It takes a query as input. A query is like a Scheme expression. It's something you type at the prompt, right? You can type a Scheme expression at the prompt and out comes a value. You can type a query at the prompt and out comes your query back again with values substituted for the variables that make it work. Well, what QEval returns is not a value. And what it takes in is not an environment, exactly. It's written to take a stream of environments. So you could think, if you had a lot of environments, you could just do them one at a time. In some situations, there are infinitely many answers to your question, or at least infinitely many potential answers. But it's worthwhile seeing them one at a time as they materialize, and you can just stop the computation when you're happy. So on the other hand, we don't want to write a program that says find something, print the value, find something else, print the value. That's not very elegant. And so what we do is we use the technique that we have for reordering computations, namely streams. So the QEval kind of on the side input here is a potentially infinite stream of environments. And in principle, we go through all those environments. An environment is a binding of variable names to values, right? Just like Scheme, basically. And we try this query on each different environment, and whatever answers we get take the form of a new environment. And so the result is a stream of environments, again, potentially infinite. Each environment, this is unlike the metacircular evaluator, each environment is just one frame. And so you should ask yourself, how can that be? Because they have a scoping problem the same as Scheme does about having a local variable in a particular rule that might be the same as a variable in some other rule. And they resolve the problem differently, which is as you're applying a rule, you systematically rename all the variables in the rule. So if the rule has a variable $foo, then for this invocation of the rule, it's going to be $foo 27 or whatever. And we substitute $foo 27 for every place where $foo appears. And the next time through, it'll be $foo 28. So there's a global counter of how many rules we've applied that are used to make these names. And therefore, every variable name is unique. It only appears in one rule. But the same variable can appear in the body of the rule and the conclusion of the rule, and it really is the same variable. It has to have the same value. OK, so an environment is a single frame. A frame is, just like a Scheme frame, almost. I'll talk about that in a second. And the input and the output from QEval is a stream of frames. Now, how could it be infinite? When you start out, well, what do you start out with? When you are typing something at the query system prompt, what's the equivalent of the global environment? And there aren't any predefined variables, because unlike Scheme, there's no such thing as a primitive procedure, because there's no such thing as a procedure, period. OK? So the things that you might be misled into thinking are procedure names, like append up there, that's just a piece of text. It's the word append. It isn't bound to anything because it's not a variable. It's as if you said quote append in scheme. It's just constant text. The only variables are the things with question marks at the front. So what we start with is no bindings. And so you might think that a good starting point would be an empty stream. But it turns out, for technical reasons, that doesn't work. And what you need to do is start out with a stream of length 1 containing an empty frame. Because nothing's going to happen unless there's an environment for it to happen in. So we start out with one environment, i.e. one frame, that's empty. Now, the way QEval modifies its stream of frames in producing the output new stream of frames, there are 3 things it can do, I think. Let me make sure I'm getting this straight. One thing it can do is take a frame and add new bindings to it. So that would be, we've already bound some variables, let's say, from your original query, and now we're trying a rule, and we match the conclusion of the rule against your query, and that works. But that gives us some new bindings, because the rule has variables in it. So we would add those bindings to the frame, and that would make a new, bigger frame. The second thing that can happen is we can do what I just said more than once. We can take the same input frame and produce several, many, maybe infinitely many, output frames. Why is that? Because in order to get from the input frame to whatever output we need, we're going to what QEval does is it tries all the assertions and all the rules to see if they match the query that you're making. And so for every assertion and rule that matches, we get a new set of bindings. And it can get to be infinite because of recursive rules. So you can end up generating an infinite stream of frames that way. And of course, as usual with streams, what's really happening is they get generated one at a time, and the next one is generated only when we force a promise by taking streamcooter. Just, when we learned about streams the other week. Okay, so I guess one thing to add to this picture is that there's kind of an implicit input to every QEval call, namely a database that contains all the assertions and rules. So whenever you say assert bang such and such, you're adding to the database. And QEval, the database is it's a global thing in the evaluator. QEval always looks through the database to look for things that match your query. Okay. Oh, the third thing that can happen to a frame in this stream of frames is that it can be rejected. You can say, well, I'm sorry, you had a partial match, and then you tried to apply a rule, and now I'm evaluating the body of the rule, and I can't match that. So this set of bindings that you've given me is not going to work. Okay, so we can add to a frame, we can add new frames, and we can remove frames from the output stream of frames. It's not done by mutation or anything. It's producing a new stream of frames functionally. So that's pretty amazing, by the way. This is all functional programming in the implementation, except for adding to the database. That's the only non-functional part of it. Okay. Now let me talk next about how a query is matched against things in the database. So we have our query like likes Brian what? Okay? And we're going to, let's say we don't have any bindings, so we don't know what is. We're going to match this against every assertion in the database. An assertion is something like likes Brian broccoli, right? So likes matches likes, Brian matches Brian. What, question mark what matches anything, so it matches broccoli. And so we make a new frame out of the old frame in which we've added a binding. So now we have a frame that says question mark what equals broccoli. And that would be one entry in a stream of frames. Okay? This kind of pattern matching is very, very straightforward and easy. Okay, if you remember the equal question mark that you wrote in the first week, I think, of chapter 2, given EQ, you were supposed to write equal for homework. Who remembers that? Okay. Match is exactly like that. It goes through all the cases. Is this a word? And if so, is that a word? If one is and the other isn't, false. If they're both words, EQ them. Are they both, is one a list and the other not a list? False. Are they both lists? Equal the cars, equal the cooters. If both of those are true, it's all equal. Match works exactly the same way, except that in the query, this is something in the database, an assertion. In the query, you can have a variable, but not in the assertions in the database. When you say assert bang and you don't say rule, you can't have any variables in what you say. It's got to be a particular thing, like likes Brian broccoli. Okay? What about rules? Here's where it gets interesting. So, in the database, I have rule. Grandparent, old, young. And that's true if and parent, old, middle. Parent, middle, young. Okay, that's what's in the database. And my query is grandparent who Brian. Okay? Okay, so when we make this query, first we go through all the assertions in the database. And let's say there are no assertions, no plain old assertions about anybody being anybody's grandparent. All the assertions are about parenthood. And we're supposed to deduce who the grandparents are. So we go through the rules and we find this rule. And the way evaluating a rule works is you match the conclusion of the rule, which confusingly is the first part of the rule, with the query. Okay? So if I do that, I say, okay, this matches. I get the bindings old 1 equals who, and young 1 equals Brian. So this is a frame that comes out of matching the query against the conclusion of a rule. But this kind of frame is something you can't get in the scheme evaluator. In the scheme evaluator, it's always a variable equals a value. And it's perfectly clear which is the variable and which is the value. And you're not allowed You know, if I say define x something or other, and then I say define y x, and you draw an environment diagram that has y bound to x instead of y bound to something or other, then you lose points, right? Variables aren't bound to variables in the scheme. Variables are bound to values. And that really, really simplifies life. Here, we have a variable bound to a variable. Even more complicated things can happen, right? So if I have a rule that has question mark u dot question mark v, and in my query, it says something like question mark, no, it says foo dot question mark x. Now we're going to go through and make two bindings. From question mark u1 to foo, and from question mark v1 to question mark x. Okay, so all of that kind of thing can happen as you're matching up queries against rule conclusions. And this is because, the reason it's more complicated, in the assertion case, only one of the things you're matching is allowed to have variables in it. In the rule case, both of them can have variables. Okay? So now, think about, remember that one of the rules here is, I don't mean rule, I mean like one of the rules, is if you use the same variable name twice, it has to mean the same thing both times, right? So if later on in this evaluation process, we make another reference either to question mark old one or to question mark who, so there'll be another binding someplace later on, and you have to be able to chase down more than one binding to get from a variable to its value. And maybe we don't know yet what its value is. So if that's the environment, we don't know what the value of old is, or what who is, rather. We know it's the same as some other variable, but we don't have an actual value for it. Okay. This much more complicated kind of matching, where you can have variables on both sides, is called unification. There's a whole section in the book about how unification works. There's a big chunk of the book about how the query system works altogether. But the part that I'd really like you to read is the part about the unification algorithm. Not because, God forbid, you're going to memorize it. It's really complicated. But I really would like you to get a feel for what it does and for how complicated it is. I would like you, for example, to be able to do a fairly simple unification by hand. So a fair exam question would be, here's a query, here's a rule, what bindings do we get when you unify them? Unification was invented, I think, in the early 70s. And as often happens, there's a dispute about exactly who invented it. There's a footnote about that in the book. Everybody outside of MIT says it was this guy in France. Everybody at MIT says it was Carl Hewitt at MIT. The reason for the dispute is that Hewitt wrote this enormously long thesis that nobody understands. It's really dense. If you think our textbook is dense, you should see Hewitt's thesis. So it's not clear what he did or didn't invent, unless you read very, very carefully. Anyway, be that as it may, the unification algorithm, all by itself, is Turing complete, meaning anything you can compute with a computer, period, you can compute with this algorithm. So we can have this query system that basically does nothing but unification, and that's all you need to compute any computable function. Okay? When I say computable, the bad news, and you'll learn this if you do automata theory, 160 or 162 or something, is that of all the functions that there are in the world, only a teeny, teeny sliver are computable. It's infinite. There's an infinite number of computable functions. But there are degrees of infinity, and this is a teeny one. There's way, way more functions that aren't computable. But if it's computable at all, that's the sense in which I'm saying that this is universal. Any function that's computable at all is computable this way. So that's what makes logic programming interesting, is the fact that it's universal. And people didn't realize it was universal until the unification algorithm came along. So you're going to read about it in the book. You're not going to try to remember how it works, but you're just going to see, boy, they sure have to deal with a lot of special cases to get this right. So the result is beautiful and elegant above the abstraction barrier when we do logic programming, but the algorithm itself is messy. OK, so that's the story on unification. So when we see a rule, we unify your query against the conclusion of the rule. If that works, the result is an extended frame, right, because we had some bindings in the course of doing this unification, and a new query, namely the body of the rule, in which case it's that and. So we're going to take and parent blah, 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 parent blah, 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 and we're going to try to evaluate, to Q-eval that, starting here, starting with these bindings. So old one and young one are constrained. Well, old one isn't really constrained. What's really going to happen is later on we're going to constrain old one, and that will implicitly constrain who to have a particular value. Young one, we know the value already, and it's got to be that to match. So we're going to end up looking for everybody who's a parent of Brian in the assertions. OK. That's an and, that body. And is special. Remember I said and, or, and not are kind of like the special forms of the query system. So we don't try to find a rule whose conclusion is and blah, blah, blah. We don't do that. Instead, we take all the pieces, and there could be, you know, in this case there's exactly 2, but there could be any number. But I'm showing you how 2 works, and you can see the obvious extension to more. And we're going to see how and or and not are evaluated. So starting with and, what I've drawn here is the initial situation when you're typing a query at the query prompt. Namely, we start with a stream. That's what these braces mean. And inside the stream is an empty frame. Now, that's not what's going to happen here. Because in this situation, this and is the body of a rule. So what's going to come in here is a stream that includes this frame. And maybe some more frames if there are more matches to other rules. Probably there aren't. But so there's going to be at least this frame where I've drawn this empty stream, this stream with an empty frame. So this is just to remind you what the initial conditions look like. But what's coming in here can be any stream of frames. And we want to evaluate and PQ. And I think this is one of the most beautiful things in the course. It's up there with tree map. Not quite, but almost. We take whatever our initial stream of frames is. We query evaluate P, the first piece of the and. The result of that is a new stream of frames, which we use as the input to a Q-eval that evaluates Q. Because what's going to come out of here is every possible way to match P, every set of bindings that makes P true. And then, starting with those bindings, we're going to look for ones that also make Q true. And that's what's going to come out the side here. So when you sort of cascade Q-eval calls one after another in this way, you're computing an and. Isn't that beautiful? Yeah? And 1 thumb up. OK, a few people like it. I love it. I don't like or so much. I mean, it's OK, but it's not mind-blowing like and. Because what we're going to do is evaluate P and Q independently. Because for or, you don't have to have one set of bindings that satisfies both of them. You're going to take any set of bindings that satisfies either of them. If it satisfies both, that's a bonus. In fact, if you've played with the query system in the lab at all, you will have noticed by now that if it satisfies both of them, you might end up with the same result printed twice. Because it means there's two ways to deduce the same set of bindings, the same frame. Okay? So starting with whatever we're starting with, in both cases, it's the current environment stream goes into both Q evals. We evaluate P, we evaluate Q. Each of those gives us a stream of frames. And now we have to somehow merge this stream of frames. How do you merge two streams? Yeah, interleave. This is why when you do a query that's at all complicated, you're sometimes surprised by the order in which the results come out. It might look a little messy. Why? Because what you're seeing is the result of an interleave. And, you know, that gets a little messy. So that's the explanation for that. OK, now comes the really ugly part. It's like the good, the medium, and the ugly. I think that would be a good movie, the good, the OK, and the ugly. And that's not. Not's ugly. And not's ugly because it can't really do the job that it's supposed to do in actual mathematical logic. So let's say I put in the database a bunch of assertions. And I say, Brian likes ice cream, Brian likes pot stickers, Brian likes the Beatles, Brian likes the Kinks, Brian likes broccoli, Brian likes the zombies. OK, that'll do. And now let me ask you, how does Brian feel about asparagus? Does Brian like asparagus? You don't know, do you? Maybe Brian likes asparagus and just hasn't bothered putting that in the database. Maybe Brian doesn't like asparagus. Suppose I ask, who likes the Beatles? How many people in here like the Beatles? OK, I don't know most of your names, so they're not in my database. So if I ask who likes the Beatles, I'm going to get not every possible answer. So if I say who doesn't like the Beatles, and if there's no dislike information in the database, it just sits there and gives me no result at all. It doesn't tell me who doesn't like the Beatles. What we can do is say something like, who likes broccoli and doesn't like the Beatles? Because we can go through the database and get a bunch of people who like broccoli. Okay? And then for each of those persons, each person, we can say, does so-and-so like the Beatles? If it's in the database, then we say yes. If it's not in the database, we don't know for sure that they don't, but we don't know that they do, and so that would be included in the result. So as far as we know, so-and-so likes broccoli and doesn't like the Beatles. All right? The upshot of this is that not never, ever generates new bindings. You never find out something you didn't know before because of not. The only thing not has the power to do is eliminate a frame, an environment, from the stream, the output stream. Okay? So not over there is a filter. It takes a frame stream, and what you get out is a subset of that frame stream. Namely, the ones for which we are not able to prove that P is true for this set of bindings. So for each frame, we run the frame through Q eval with the query P, And then we say, okay, was the answer to that empty? No frames? If so, then the original frame that we started with goes in the result. If we do have a frame in the output, which means we did find a way for P to be true, then we remove that frame from the output. So anything that could make P true, we eliminate. That's what not does. So this is why it's pretty much guaranteed that if you just type at the query prompt a query that starts with not, you're not going to get any output at all. There has to be some variables bound in order for not to do anything. And there are two ways that can happen. One is that the not is in the body of a rule, and the conclusion of that rule matched your query, unified with your query, and that produced some output frames. Or the not is part of an and it's not the first clause of the and. And the first clause of the and created some bindings, some constraints on the values of variables. And then the not comes along and it says, well, okay, you said you can handle this, this, and this set of environments, but sorry, I'm rejecting this one and that one. We're only keeping this other one, namely the one for which P cannot be satisfied. Questions about that? All right. If you're confused about this, it's okay. You're just learning about it. The book talks about it at length, about the problem of not. And why, we can't just exhaustively be sure. Now, footnote. Sometimes we are dealing with a known finite universe. Okay? So, like, there's only 4 people in our universe. They're John, Paul, George, and Ringo. And we put in some assertions about them, like, John wears glasses or something. And then we can say, is P one of John, Paul, George, or I'm sorry, not P, is X, person, one of John, Paul, George, or Ringo, and not such and such. So if you're in that kind of situation, then you can sort of find out all the not cases, provided that you know everything there is to know about, or everything that's interesting to know anyway, about those 4 people. That comes up sometimes in logic puzzles. So one of the things you'll see maybe in the book is trying to solve, who lives in the yellow house kind of puzzles in the query system. And you can't solve them unless you tell the query system that everybody has to live in the yellow house or the green house or the blue house or the orange house before you give it the particular clues that you have. All right, so and, or, and not. Let me try to sum up everything. This is an imperfect abstraction in the same way that streams were an imperfect abstraction. Remember we said sometimes you had to put in explicit delays, right? And we could fix that by having a normal order evaluator. This is an imperfect abstraction also. And as far as I know, they haven't really fixed it. They've worked around it. And the workaround is in Prolog, which is the logic programming language everybody uses. There's a thing called cut. It's another special form. It says, don't go down this branch. If you just matched this, don't try to apply this rule recursively. And that way, if you think about the order in which things happen, you can prevent infinite loops in your queries, in your rules. Okay, so that's one thing about logic programming. Another big thing is unification. Unification was a huge step forward in computing. It was a non-obvious invention. Nobody knew it could be done, let alone how to do it, until somebody did it. And it's at the heart of making logic programming work. It is the only algorithm, basically, in the query system. So in every other kind of programming that you've seen, where do algorithms come from? They come from you, the programmer, right? For every particular problem that you're trying to solve, you invent an algorithm for solving it. In a query system, you never talk about algorithms. You never say, first do this, then do this, and so on. Or, you know, what's f of g of h of 23? You don't do things like that. Instead, you just say, here are some things that are true. And the query system uses its one algorithm, unification, to find amazing results, including the ability to kind of work backwards if you think about it in functional terms. But it's not, the query system doesn't think of it as backwards because in that set of rules for append, the 3 slots that go after append, you know, they're all just data. It's not like one is privileged in some way. Okay, so unification. 3 is the difference between eval and qeval. I'd really like you to understand this, that when you ask a question in Scheme, you get one answer, because what eval gives you as its result is the answer to the question you asked. You know, what's the square root of 49? It's 7. Thank you. But in the query system, you can get multiple answers, maybe infinitely many answers, just because of the way the algorithm works and the way rules can be recursively applied, even though they're not procedures. Okay, so qeval, therefore, doesn't return an answer. It has to somehow handle the fact that there might be infinitely many answers. And the way we handle situations with infinite data sets is using streams. So here's an application of streams. You wouldn't have to do it this way. Just as when I first started talking about streams and I wanted to know if a number was prime, you could write that little loop. Let you know, I equals 2, blah, blah, blah. Try I plus 1, and keep going like that. You can do the same sort of thing for inventing a query system. But the cool functional way to do it is to use streams. And it means that as you read the program, we're doing the evaluation for all the different possibilities in parallel, kind of, even though it's not really how it happens. So at the very end, think about the read eval print loop in the query system. It can't just be print qeval of blah, 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 because qeval doesn't return anything printable. It returns a stream of frames. So what the read eval print loop has to do is keep cootering down that stream of frames, taking each element, and remember each element is a set of bindings, and then looking in that set of bindings to find the values of any variables in your query. And again, that might involve chasing down a whole bunch of bindings, because your variable might be bound to another variable, which is bound to another variable, which is bound to another variable, which is finally bound to a value. And it has to be able to work its way through that and get to where it has values for all the variables, if possible, and then print that. So the read eval print loop is a little more complicated than it is in Scheme, because that's where you turn this stream of frames into something a human being can read. Okay? Any questions? What's the point? Who thinks logic programming is really cool? Good. Who's totally lost? A few people. All right, totally lost people. See what your TA has to say in section. Ask me questions. You can ask questions now if you have any. You can come visit me in office hours. Again, you're not expected to know every detail of the implementation, but I would like you to read through the details of unification, which is the thing at the heart of the system. Okay, now, In my lecture notes, on the next page, which is page 372, is an example involving append completely worked out. So the question is, append what to get this two-element list, AABB. I used AA rather than A so you don't get it confused with the variable A, which there also is one of. So here's my query, and we go through all the steps of calling unify match. Unify match takes 3 arguments: the query, the conclusion of a rule, and a stream of environments. Oh, no, I'm sorry, an environment. QEval knows about a stream of environments. The unification algorithm knows about only one frame at a time. So it's an environment. So it starts out being the empty list in this first evaluation. Now, once I actually tried going through this in lecture, all the students fell asleep. So I'm not going to do that. But if you're the kind of person who really needs to see step by step how something works, it's not so difficult to go through this and work out for yourself. There's 1, 2, 3, 4, 5, 6 calls to unify match in here. So, 6 is a pretty big number, bigger than I would want to do in lecture, but it's not 500 or anything. Yeah? Where are you likely to see the query system in the wild? That's a good question. Europe. Remember I said invented in France? Americans, for some reason, mostly aren't very interested in logic programming. There are little exceptions here and there. I'm not sure if it's still true, but I think it is. UW, University of Washington, is kind of a hotbed of logic programming. The closest thing to it that you'll see in the wild in this country is database query systems like SQL, which are very similar in spirit to this. At one time, the government of Japan had a regulation saying that all the programming for, I think then we were up to 4th generation computing, was going to be done in Prolog. It's just like in this country, the Department of Defense has a rule that if you want to program anything for them, it has to be done in Ada, which is this really terrible language. Don't tell Paul Hilfinger I said so. He likes Ada. It's just so big and... But anyway, in Japan it was Prolog, and they've backed off from that. But you see a lot of still Prolog code in the wild there. Best I can do. Other questions? It's not. All right. On Friday. Oh, yes. Go ahead. Is it massively inefficient? No, because of the reordering and the memoization of streams. So it's much more efficient than it looks. Yeah, no, it's not bad. Was that a hand up, or are you yawning? He's yawning. OK. On Friday, we're going to try to attempt a review of everything. Please bring to lecture on Friday something to write with and something to write on. I'm not collecting anything, but you're going to do an exercise. Your computer is fine if that's what you have, but some way to write things. And I'll see you Friday.